Welcome to this session. My name is Renee McCormick. I'm with the National Math and Science Initiative, and I'm really glad you're here. This is the third and final installment in the chapter that is typically Chapter 4 in most AP Chemistry type, university type chemistry books, and it's called Types of Reactions and Solution Stoichiometry. So, oxidation reduction reactions are something you may or may not have seen before. If you had a really stellar first year chemistry teacher, they may have gotten this far, but overwhelmingly, first year chemistry teachers can't make it this far in their textbook because of state tests and all sorts of interruptions along their journey. So this may be brand new information, and if so, you may want to listen to it more than once because the next chapter we're going to cover is electrochemistry, where you're going to have to apply all of this newfound knowledge. So you want to make sure you're good at this before you kind of get sucked into what I call the knowledge of the black hole of knowledge. And if you miss out on not being able to do the ABCs, it makes it really tough to spell. And so that's kind of where we are with this. This is like the ABCs of electrochemistry. So terms to know. There are all sorts of different little mnemonic devices, fun little ways to remember things, like Roy G. Biv gives you the colors of the rainbow sorted out by wavelength. So oil rig, oxidation is loss, reduction is gain. What are we losing and gaining? We're losing and gaining electrons. Oxidation is the loss of electrons, and that causes an increase in charge, while reduction actually makes sense to your math brain. It's the gain of electrons, which you know are negative, so it's a reduction in charge. So I often start here. When I get a choice, my brain's going to go there first and realize that the other one is where there's an increase of charge. Because the word oxidation doesn't really give me that mathematical clue. Oxidation numbers you probably already know. These are the assigned charge on an atom. And if you think back to your formula writing days, you had to learn a few of these rules to be able to write formulas successfully. So if we take just a moment to look at the periodic table, you can bet that the 1A column with lithium, sodium, potassium, etc., those 1A metals right there, are going to be plus ones, and that the 2A's, the alkaline earth metals, are going to be plus 2 most of the time. Aluminum is sitting over here at a plus 3, and so most of this column follows suit. Then I skip the 4s because they can do all sorts of different things, so don't be alarmed. They can be plus 2, minus 2. They can do all kinds of things. Very easy to get along with. And then nitrogen typically is a minus 3, but there will be times when they also can be positive. So the nonmetals can do different things, shall we say, than metals, which always lose electrons. And then oxygen is going to be a minus 2. We have a rule for that, as you're about to see. And halogens are almost always a minus 1. But again, a good friend of mine said that Chem 1 is like teaching all the generalities, and then when you get to AP Chemistry, it's like teaching all the exceptions. So don't be alarmed. If you find yourself scratching your head, it's probably got a different oxidation state than you're expecting. But we've got a couple of rules that's almost like a hierarchy that we'll start with those first every time, and we'll try to avoid most of these pitfalls. Then you know the transition metals can be all sorts of different things, and that's why you use Roman numerals to indicate their charge. So they shouldn't surprise you at all when they're doing all sorts of weird numbering systems for their oxidation numbers. All right, so those rules, speaking of the rules, notice it's a short list. The oxidation state of an atom in an element is 0. So you're always on the lookout for the elements. Don't forget about the allotropes, things that are diatomic. Nitrogen, well, the gens, hydrogen, oxygen, nitrogen, and all the halogens are all diatomic. But phosphorus has a tendency to be P4, and then sulfur has a tendency to be S8 in their allotropic form, where they cluster together as a clump of atoms. The oxidation state of a monatomic ion is the same of its charge. Smiley face, that's easy. If you write Na+, then its oxidation state is +1. If you write S2- for the sulfide ion, its oxidation state is -2. It's a no-brainer. I don't have to think that hard. In its compounds, fluorine is always an oxidation state of -1. If it's an element, we're back to rule 1. So have you ever seen those t-shirts that say, rule number 1, mom is always right. Rule number 2, if mom is ever wrong, consult rule number 1. This is kind of a hierarchy in the same way. So fluorine's always assigned an oxidation state of -1, unless of course it's an element, when rule 1 trumps that and says then its oxidation state is 0. That would be F2. Oxygen is usually assigned a -2. The word usually always means trouble is coming. So if you think about CO, CO2, SO2, and SO3, All of those we have assigned -2, so that means carbon is +2, carbon is +4, sulfur is +4. That 4 didn't come out very good, did it? And here sulfur is +6. Exceptions are the peroxides. So if we look at hydrogen peroxide, our good buddy H2O2, which is not the only peroxide in the world, it's just the most common. This entire critter right here is the peroxide ion, and in this case we have a -2 on that whole group. So it's a -2 on the peroxide ion. So each H is still a +1, and that's why H2O2 is neutral. And then we can also have OF2, in which case F is always -1 in a compound, so this whole side over here is a -2, so that oxygen has to be a +2 to make that work out. Then, in its covalent compounds with nonmetals, hydrogen is assigned an oxidation state of +1, but it also is a freakazoid when it's a hydride. But you're going to know this because it's going to have a metal in front. So if I have sodium hydride, it looks like that. So the sodium is going to be the +1, and the hydrogen can be the -1 because it gained an electron. And so where'd the electron come from? We know that sodium likes to be a +1 ion. So these are pretty unstable, as you might imagine, because that one proton of hydrogen doesn't do a very good job of hanging on to 2 electrons. That's a tricky business. All right, then the sum of all the oxidation states must be 0 for an electrically neutral compound. And for a polyatomic ion, the sum of the oxidation states must equal the charge of the ion. So let's practice a little bit. You knew that was coming, right? All right, so I'm going to write these nice and big. CO2 as a molecule, SF6 as a molecule, and the nitrate ion with a charge. So what we're saying here is that we have a rule that says an oxygen is going to be a -2 each. So that means this carbon is going to be a +4. Think about it. 2 minus 2s is -4. Only one carbon, so it has to be a +4. Fluorine is a -1 in its compounds, and there are 6 of them. Only one sulfur, so it's got to be a +6 to make that work out. Now this one's a little more fun because instead of they just cancel out and so that their sum is equal to 0, now we have to contemplate the fact that the sum has to be the charge, so it's got to be a -1. So we still know that all 3 of those oxygens are -2, so that's a -6 so far. So what do I add to that -6 to get a -1 for the total? Not a trick question. +5. Are you smarter than a 5th grader, Jeff Foxworthy math? So that nitrogen then is a +5. Don't you wish all of chemistry was this easy? Now do beware that on occasion something in a book or on the internet or in a text could be a typo, but sometimes they'll just make you scratch your head when they're not a typo. Beware that there can be non-integer oxidation states. So if I look at Fe3O4, we have a rule that says that oxygen is going to be a -2. So that's a total then of -8. Well, how do you take -8? I got to have a +8 over here on this whole piece because there's only 2 pieces of this molecule. So that's got to be a +8, but how the heck is that going to work among 3 of these? So its oxidation state would be written as 8 divided by 3, positive 8 divided by 3. But the reality is that's not how this works. If you've got 3 irons, remembering the iron is a transition metal, right? Iron's sitting right here in the transitions, right there. So that transition metal can be all sorts of different things, 2 and 3 being the most common. So if I had +3 and a +3 and a +2, that equals 8. If I had a +2 and a +2 and a +3, that equals 7. So that's not the story. This is the story. But its oxidation state is 8/3. Now, you're probably never going to see that again, but just in case you run across it in a homework problem in your book somewhere, I didn't want you to think that I had not given you the complete story. All right, exercise 17 in this chapter. Long chapter, huh? When powdered aluminum metal, woohoo, that's an element. So aluminum's oxidation state is 0. Is mixed with pulverized iodine crystals. Woohoo, that's an element too. Pulverized just means I've squished them up. Iodine crystals means that's an element. Aluminum metal, that's an element. So I already know what their oxidation states are. A drop of water is added to help this reaction get started. So was the pulverizing to make greater surface area versus volume ratio on the iodine crystals. The resulting reaction produces a great deal of energy, excitement in your future. The mixture bursts into flames, that would be the exciting part, and a purple smoke of iodine vapor, which is your clue to run for the hills, get that sucker in a fume hood, or get it outside, because if you inhale iodine vapor, it will damage your lungs, so run, is produced from the excess iodine. The equation for the reaction is, for this reaction, identify the atoms that are oxidized and reduced. All right, so what did the aluminum do? It went from 0 over to a +3. So that is oxidized, which means mathematically the number increases, as opposed to, go ahead, guess what reduced means. It's the one that makes sense. This one started out at 0 and ends up over here, 3 of them, so they are -1 each. So the number went down from 0 to -1, so that is reduced. Easy enough. See, not everything has to be painful. Metallurgy. The process of producing a metal from its ore. That's what the mining industry in this company was built from. Always involves oxidation reduction reactions because you're trying to get this chunk of rock to actually give you the metal itself. It's just that we see 2 chemical reactions here, so it's a 2-step process. So in the metallurgy of the mineral galena, which is what we usually call something that we've dug out that's an ore from the Earth's crust, mined for it, shall we say, it's the principal lead-containing ore. The first step is the conversion of lead sulfide to its oxide. And notice that there's no Roman numeral in there the way it should be. So again, we're probably talking about a mixture of lead 2 and lead 3 as ions, but we're trying to get lead 0, which is the actual metal, out of this. That's what we want our end product to be. So sulfur is usually a -2. Again, look at the periodic table. It's oxygen's cousin right here in the oxygen family. So they're usually -2. Not always. That's why I say usually. When I get to say always, it is a celebration. So that means this lead is a +2. Whereas oxygen is an element, don't overthink that. That oxygen's a -2, so this lead is a +2, so nothing's changed with lead there. But look at what's going on with sulfur. You have -2 on each of those oxygens, so that means that sulfur is a +4. Now we're talking. What has gone on? Well, this oxygen right here at 0 has been reduced to a -2. What else has happened? This lead at a +2 is staying at a +2. Nothing exciting there. But this sulfur as a -2 is coming over here to be greatly increased up to a +4. So that's my oxidized. This was not exciting. So don't be alarmed if you have things that look like they're going to do something and it turns out that they don't. All right, then what's the next step? Well, the oxide is then treated with carbon monoxide to produce the free metal. All right, so let's start with that. This lead is a +2 because that oxygen's a -2. Oxygen's a -2, so that's a +4. A 0. Okay, zeros always means something probably happened here. All right, then this is a -4, so that's got to be a +4. So the oxygen's -2 each. I'll write it that way. But there's 2 of them, so +4. So what's the story here? My brain likes to start with the reduced. So lead was a +2, and it has gone down to be 0. So it's reduced. And so the oxidized is going to be my carbon, because nope, it's +4 on both sides. So what's going to be oxidized? No, that's not right. It's +2 over here. I wrote +4, but that's a lie. Look at that. -2 and +2. Please forgive. So that's going to go over here from a +2 up to a +4. So that's my oxidized. I'm sure you can make that look prettier than I did. So let's get the summary. oxygen is reduced. I like to do reduced in red. Try to figure out why. It's reduced. So oxygen is going to a -2, and lead in the second step is reduced from a +2 to a 0. And then sulfur is oxidized, so it's a -2 going up to a +4. And then carbon. If something's going to be oxidized, something else has to be reduced. +2 going to a +4. You can't have one without the other. They are partners in crime. Now, you got to be able to do that. So if that lost you in any way, or if you're scratching your head, pause me now. Pause me now and do one of two things. Go out to that new thing called the internet and find some examples of assigning oxidation numbers that you can get the answers to because they're right there on the internet. Or use your book. If you have your book at home with you, look at the back of the chapter. They're going to give you several sample problems. You know that the answers to some of them are probably in the back of the book so that you can check yourself and practice that skill a little more. I'm going to move on and teach you how to do balancing redox reactions by what we call the half reaction method. Oh yeah, it wasn't bad enough that you had one reaction to balance. Now we're going to split it into two halves so you have two of them to balance. But again, you should find comfort in the fact that we have steps. I can't always give you a step-by-step, blow-by-blow, how to solve a problem sort of recipe. So take advantage of this. Step 1, and you should do it first because it's step 1. You divide the equation into oxidation and reduction half reactions. So the exercise we just went through, where I drew my little arrows and such, these little boxes of sorts, these things right here, that's my way of kind of making you visually understand what's being oxidized and what's being reduced. So you got to do that first. Then balance, and you don't have to do the boxes. You just have to figure out what's being oxidized and what's being reduced. Then balance all the elements, leaving hydrogen and oxygen for last. Do those last because we have some more rules coming that make that a much easier task. Balance the oxygens by adding waters. Balance the hydrogens by adding H+. So you can add these things as much as you need to. If you start adding them to both sides, you've done something wrong. So wherever you have an excess of O's, you put waters on the opposite side to introduce the O's until you get even again. Wherever you have an excess of hydrogens, you put H+'s on the opposite side of the arrow until you get even again. Then, after we've done that, we've introduced some pluses into the situation, so we need to balance by charge. And we do so by adding electrons. No, you cannot subtract electrons. No, you cannot add protons. Chemistry happens only with the electron cloud. You leave that nucleus alone. Do not try to put in neutrons or protons into these equations. All about the surface where the chemical reactions take place with electrons moving from one substance to another. Then we got to do our accounting part. That's when we will multiply the half reactions to make the number of moles of electrons equal for both half reactions. So you may find yourself into what I call a 2-3 trick because you got a 2 on one side and 3 on the other, and you got to get to 6. So you have to multiply the one with 2 all the way through everything by 3 to get to 6, and you got to multiply the one with 3 all the way through by 2. I may have just said that wrong, but you know what I mean. 2 times 3 so that you can get to 6. Then cancel out any common terms. Any common terms, which would be your electrons because that was the whole point. And then recombine the two half reactions. Repair the damage, in other words. Now, everything to that point has been an acidic medium. It's another word for environment in chemistry. Alright, so that's all an acidic medium. So if it says in basic medium, you will find a whole nother set of rules in your book for that. But you know, I'm way too lazy for that. I'm not going to memorize 2 sets of rules if I just got a quick fix. I'm going to memorize 1 through 6, no problem. I'll practice enough, that'll become second nature. If it's basic, all I have to do is do it exactly the same way I do acidic. It's just I can't have any excess H+'s at the end or I'm a dirty rotten liar because that's going to be an acidic situation, not a basic. So I'm simply going to add however many OH minuses it takes to make waters. And then to the other side, I will add the same number of OH minuses. So I'm going to say X and X. So those are the same. So I'm going to have excess hydroxide on the opposite side that I had excess H plus on, because these again are going to become H2O. And I may have to do a little water cleanup at the very end. And the very, very last thing you want to do is check, because this is one of the easiest things to check. There are many ways to check. The book will tell you to do it atom by atom by atom in these long lists. I'm way too lazy for that. No, if you'll just check the total charge on the left and the total charge on the right, you can rest assured that you have got it balanced. So shall we? Shall we try a sample problem? I think we shall. All right, assign oxidation states to all the atoms in the following equation, identify the oxidation reduction half reactions, and go ahead and balance the sucker. So, MnO4, I have to get it down here nice and big so I can write all over it, plus iron, 2 plus ion, gives me a manganese, 2 plus ion, and an iron, 3 plus ion. Okay, it looks weird already because there's O's on the left and no O's on the right. But that's okay, we'll fix that. Next thing I want to do is I want to get the oxidation states over here. I know that this oxygen is a -2 because I've got a rule for that, and there's 4 of them, so that's a total of -8. But the whole ion, the permanganate ion, has a -1 charge, so I know then that this Mn plus it's got to be a +7 to make that work. So something was reduced. I always start there, but you can do this any way you want. You can start with the oxidation if that makes more sense to your brain. So I start with the reduction. Well, that +7 going to +2 is a mighty good reduction. So pick up MnO4 minus and go to Mn2 plus. Well, see that 4 O's on the left and nothing on the right? You fix that with waters. How many waters, you ask? Well, how many O's do you need? I need 4 of them, so I got to use 4 waters. Well, now you've gone and done it. Now you've introduced 8 H's that you don't have over here on this side, but you have a rule for that. You can add as much H plus as you'd like. 8 is an excellent number to get that to cancel out. So now what have I got? I have MnO4 minus plus 8 H plus, Mn2 plus, and 4 H2O. So by element, everything is balanced. 4 O's on each side, 8 H's on each side, 1 Mn on each side. But charge is a hot mess. So I need to fix that. What's the total charge on the left? Use all your fingers and toes if necessary. I'll wait. What? +7? Indeed, +7. What's the total charge on the right? Water's neutral. Yeah, +2. That's all you got. So that means I've got to add 5 electrons to reduce that +7 down to a +2 charge so that it's balanced. Note, I did not go all the way to 0. That's not the goal. The goal is to get the charge balanced, not to get the charge to 0. That's a different goal. So there's my reduction half. I'm happy with that half. On to the next. Oh, those irons are a mess. Okay, so my oxidation is going to be Fe2 plus goes to Fe3 plus, because oxidation is an increase in oxidation state, while reduction is a reduction in oxidation state. In our case, it was the manganese at +7 being reduced down to +2. This is a +2 iron going up to a +3 iron, so the only thing I have to do here is add an electron. Now, next step, we want to get rid of these electrons. How are we going to get rid of them? I got 5 in the reduction half and only 1 in the oxidation half, so I need to multiply everything here. There's nothing there, Renee. Everything here by 5 so that I can do that. That's the goal of that game. Now then, let's sum that little sucker up, and I get MnO4 minus plus 8 H plus 5 Fe2 plus yields 5 Fe3 plus Mn2 plus ion, no longer in the permanganate ion, and 4 H2O. So I can kind of look at that real quick and tell you I'm balanced by element, but the fast way to figure out if you're balanced overall is to add up the total charge over here on the left. A -1 and +8 reduces that down to +7, and then I have 5 times 2, which is another 10. So what is the total there? Isn't that 17? And then what do I have over on the right? 5 times plus 3's, so that's plus 15, and plus another plus 2 is 17. So voila, we are balanced. And there you have it. All right, let's look at our next sample problem. Again, we have the permanganate ion. I'm going to start with the reduction half. This is going to be a plus 7. Why? Because 4 negative 2's is negative 8, but the total has to be a minus 1. I only have one critter, the manganese, there to do that with, so that's a plus 7. And it's going to be going to a plus 2. Hopefully I fixed that little typo and you have a plus 2 sitting there. And then that's going to be my reduction, without a doubt. MnO4 minus goes to Mn2 plus. But I've got 4 O's on the left and none on the right, and the only thing I can do about that is to add water. I can add as much water as I want, so 4 of them would get me 4 O's. But now I've got 8 H pluses that I need to add over here, because those are my rules. I can add as much water as I want. That fixes the O issue. But dadgummit, you introduced 8 H's. So adding the H pluses to the other side fixes that issue. Now, this permanganate is a plus 7. That Mn in that permanganate ion is a plus 7. So I'm going to have to add 5 electrons to this side to make plus 2 on both sides. All right, if you don't like looking at it that way, then look at the whole charge. Look at the permanganate ion as a minus 1, and I have 8 H pluses, so that's plus 7, and I have plus 2 on the right, so I need to get the left down to a plus 2 by adding 5 electrons. Two different ways to think about it. They both work. Choose. Pick what you like. The other thing I have going on is the oxidation half. So I have I minus going to I2. That's a 0 because it's an element. And this is a minus 1 over here because it says so with that minus sign right there. And so I need 2 of them. I have to balance by mass first. The first time we've encountered that. So let me say that again. I had 1 I on the left, but 2 on the right. So I have to double the I minus, which doubles the charge as well. So I have to add 2 electrons. That's the only way I can do the charge. I can't subtract electrons, and for the love of God, you cannot do anything with protons. Chemistry happens at the electron level, not the proton-neutron level. That's nuclear chemistry. This is just ordinary, aqueous chemistry. Okay, so now I have what I call in life a 2-5 trick. 2 prime numbers. 5 is a prime number, 2 is a prime number. There is nothing I can multiply either by to get the other, so I have to multiply them essentially by each other. So we run into what I call the 2-3 trick a lot, and this is what I call the 2-5 trick. So everything up at in the reduction half has to be doubled, multiplied through by 2. So that becomes 2, that becomes 16, that becomes 10. This becomes 2, and this becomes 8. Everything on the oxidation half has to be multiplied through by 5, with the goal that that's going to make that 10, that's going to be 5, and that's going to be 10. Because the whole point was to be able to do this and cross off those excess electrons and add everything else up and reduce to lowest terms if necessary. So when we do that, let's collect all this stuff and see what we got. 2MnO4 minus plus the 10I minus plus 16 H pluses yields 2Mn2 plus 5I2 plus 8H2O. Did I get everything? I believe I did. What is the total charge over here? 2 negative 1's is negative 2. Negative 10 for the 10 iodides plus 16 positives for the 16 H pluses. What does that add up to? Isn't that plus 4? Plus 4 on the left. And over here, oh, easy. 0, 0. They're not ions. 2 times a plus 2 is a plus 4. So all I had going on over here was a plus 4 and check. Now you can go ahead and do atom by atom. Your book's going to do it. Your teacher might even make you do it. I'm not going to make you do it. I know that if I can get the same number of charge on each side, I'm balanced. Save myself a lot of time and energy. Go ahead. You can admit this is just almost fun. This is like figuring out a puzzle. All right, potassium dichromate is a bright orange compound that can be reduced to a blue-violet solution of Cr3 plus ions. Under certain conditions, potassium dichromate reacts with ethyl alcohol as follows. And thankfully, they gave me all the players in this reaction. So we got to figure out who's reduced and who's oxidized. That's where you always start. I like to start with the reduction, but you don't have to. So I'm looking at a whole. Carbon is always a possible suspect, and anything to do with a polyatomic ion is as well. So let's see what we got going on here. Hydrogen's oxidation state is its charge +1, but dichromate, these 7 oxygens are all -2, so that's a total of -14. But the total has to equal -2. So I've got -14 so far. What do I add to it, 2 of them, to make that work out? So I need a total of -12 charge, so that means these are +6 each. So let me do it. Can I do it at the bottom? These are -2, and these are +6 each. All right, then I know that I've got -6 going on over here. I'm sorry, I've got +6 going on over here with these hydrogens, and I'm +6 with the hydrogens, and then a -2 with the oxygen, which leaves me with a +4, but that's split over 2 carbons, so they are +2 each. You will have to use all your fingers and toes if necessary. This one's lucky. We're lucky here because that is its charge. And that carbon is a +4. Think about it. And you know that hydrogen's a +1, oxygen's a -2. All right, so who was reduced? Definitely that 6+ going to 3+. So what you want to write for your half reaction is grab that ion, Cr2O7, 2- overall charge, and go to Cr3+. Won't you need 2 of them? Yes, you will. All right, then what? I've got, so that's balanced that. Those 7 O's are still problematic, so I have no choice but to put 7 waters over here. And 14. Why 14? Ask yourself. You can figure it out. H+ is over here. Now, what's the total charge on the left? 14 pluses and a -2 is a +12. And on the right, I have a +6. So I got to reduce that +12 down to +6 by adding 6 electrons. I'm just following the rules in order, not getting creative. Let's see what's going on with the oxidized half. Well, H+ is staying H+ on both sides. And maybe it doesn't look that way on the page, but you know that it's +1 on each side. And with these hydrogens in here, in the ethanol, what have I got going on? It's that carbon. That carbon is a +2, where this carbon over here is a +4. So it is indeed the C2H5OH, which was my only other logical candidate, that's going to be oxidized to CO2. So step 1, I got 2 C's on the left. I got to fix that. So now I've got 4 O's on the right and only 1 on the left, so I'm going to have to introduce 3 waters. But now that introduced 6 H pluses. No, I've got way more than 6 H pluses because there's 6 of them sitting over there in the ethanol as well. And so that's 5, 6, and 6 is 12. 12 H pluses over here on this side. Total charge on the, I got everything balanced by molecule now, or by element, I should say now. So I got 0 charge on the left, +12 on the right. I need 12 electrons. Now, you got 6 electrons in the reduction half. You got 12. So what to do? What to do? Double everything. 28. That's kind of nuts. So when I double this, that becomes 12. And this becomes 4. And this becomes 14. All right, so what's the story? What the whole point of that was to be able to go wham, 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 and cross through those 12 electrons. Can I clean up anything else? Oh, you betcha. I can get rid of those 12 H pluses and take 12 away from this so that they become 16 H pluses. I can get rid of these 3 waters, and this becomes now 11 waters. So let's see how that worked out. 2 Cr2O7 2- ions plus C2H5OH plus 16H plus. I think I got everything. goes to 2 CO2s plus 4, not 2, 4 Cr3 plus 11 waters. And you ask yourself, what's the total charge on the left? What's total charge on the right? I can do the right pretty easily. It's plus 12. Please be plus 12 on the other side. 2 negative 2's is a minus 4. 16 plus 1's, I'm feeling good about this, is 16 plus, and that is equal to a plus 12. Check. If you don't believe me, go ahead, count the elements. Go for it. Knock yourself out. Just make sure you do the distributive property of mathematics correctly as you distribute the 2 across here and across here, and the 11 across here and across here as you count. All right, ladies and gentlemen, I have time to torture you with one final example, but this is a good one because this one is done in basic solution. So we need to figure out what is the nuance here. What is it that we do differently in a basic solution than an acidic solution? My answer to you is one little bitty thing at the very end. I cannot have any surplus, excess H plus ion in solution. So wherever I do have that extra H plus ion, I simply go and add that many OH minuses to both sides. For instance, on this last one right here, we had 16 H pluses in excess, which was fine because it was in acidic medium. It didn't matter. That was just perfectly acceptable. But I would come in and add 16 OH minuses to both sides to make 16 waters, which would then cancel out 11 waters, leaving 5 waters and a surplus of 16 OH minuses on the other side. Clear as mud. Don't give up on me. Hang on. We're going to do it with this example. Because indeed, you always want to be on the lookout for the fact that this says in basic solution. Okay, so element, happy dance, element, happy dance. We know those are both 0. We also know that the cyanide has a -1 charge because it's written right there. And what we do see that's a little odd is I have oxygen over here and none over here on the right hand side. I've got silvers, I've got cyanides, but no oxygens. All you can really do is put some water in here. You'd be adding that in the half reaction process anyway, so it remains to be seen how much, but don't panic. You just have to think about it, that you're going to actually have some water, because all you would have seen so far is that the cyanide remains a -1, so it's really not participating in this. But the Ag is going from the 0 oxidation state to the fact that each one of these cyanides is a -1 and you have 2 of them, so it's a +1. So what's going to be reduced is going to be my oxygen. And so that's going to make water. How many waters, you ask? Not a trick question. If you have 2 O's, you need 2 waters. That forces you to add 4 H pluses over here. And so then the right-hand side of your equation is balanced, right? 4 H's and 2 O's. So I need, reduction is gain, I need to gain 4 electrons. And that's balanced nicely. So let's move on to the other piece, the oxidation piece. The oxidation piece is to take the silver in its metallic elemental form and convert it over into the complex. Now you don't know it's a complex. I've used that word twice now without explaining that to you, and that's just not very nice. So when I see something where it's all clumped together like this, a metal and then often another ion of some sort together, and the whole bloody mess has a charge on it, that's what we often call a complex coordinated ion. You will sometimes see it in a book with brackets around it, which don't mean molarity. When you see the charge on the outside, it means that's a complex. In some books, you'll see it without that, because right up here it's written without that. It just depends, but I don't want one way or the other to trip you up. It's just, again, that grown-up conspiracy with grown-ups who cannot get along. So that's going to force me to bring that cyanide ion down here and put 2 of them in there to keep this balanced by mass. And now we are balanced by charge, and we need to figure out the electron situation. So what is the total charge on the left? I have 2 cyanides, and so that's a -2, and then I have only 1 minus charge on the right-hand side, so I've got to add an electron to make that work. All right, so let's see what kind of mess we got going on now. Next step is that we have 4 electrons up here and only 1 here. Well, that's easy enough to fix. That becomes 4, that becomes 8, that becomes 4, and that becomes 4. Did I get all that correctly? I believe so. All right, so now what's left? Now we can just add this little sucker up. And what do we get? We get an oxygen. That's not very pretty O, is it? An oxygen and 4H plus. That's going to be trouble because this is in basic medium. That's trouble. Get to it in a second. The whole idea here was to cross off those 4 electrons. So I've got everything in red on the left-hand side down here, so I need to add the 4 silvers and the 8 cyanides. 2 waters and 4 of the complex. And again, you can write it with or without those brackets, and I don't want you to sweat this. Alright, so just remember that it's got a -1 charge on it. So now, this little starred H plus is a lie. We cannot have that present. That's just a lie because it says it's in basic solution. So it's not a problem. We just make them waters by adding 4 OH minuses to both sides. So this is no longer 4H plus and 4 OH minus. It drops out and is replaced with 4 waters. Now, do we need to do some cleanup on the waters? Yes, we do. I have 4 on the left and 2 on the right. I can lose all of those, and this gets reduced down to 2. So allow me to finish this off by writing it pretty. So my final answer is oxygen plus 2H2O plus 4 silver atoms. I'm going to put the O in there for emphasis. You don't have to. 8CN. You must put that minus though. 4 AgCN2 minus charge and 4 OH minus. So on the left over here I have 4 minuses and 4 minuses for a total of -8. What do I have going over here on the right? Neutral, 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 8, -8. Check. So this, ladies and gentlemen, is my final answer. Now, again I say, go forth and practice. We didn't spend a lot of time on this, but we spent, I think, enough time to get you started. So you should be able to find lots of things on the internet or else in your text where you have the answers and you can practice until you feel comfortable with this. This skill will not be going away. It's something that you want to know how to do. Thanks for your kind attention. I hope you have a great rest of your day.